Hello viewers, I Nilofer Zirgam welcomes you to the episode on statistical decision theory. In this session, an analysis is developed to determine optimal strategies when a decision maker is confronted with several alternative courses of action and a risk-filled pattern of future events. We'll discuss the different types of decision problems and describe a decision problem in terms of decision alternatives, state of nature, and payoffs. Before proceeding to study various topics of statistical decision theory, we'll first acquaint ourselves with the terms which are going to be used in the discussion. Decision analysis, a systematic approach to solving decision problems optimally under conditions of uncertainty. It does not describe how or why an individual makes a decision. Rather, it prescribes a decision for the individual that is consistent with his or her preferences and attitudes towards risk. We'll see the different types of decision problems. Although all decision problems involve the selection of a course of action from two or more alternatives, we can classify them into one of the three categories. First one, decision making under certainty. If a decision maker is faced with choosing one action from among two or more alternative actions, when the outcome of each alternative action is completely known, the decision maker is said to be faced with the decision making with certainty. Thus, decision making under certainty entails the selection of a course of action when we know the outcome each alternative action will yield. Decision problems of this type are not discussed in this text, but here is a simple example of this type of a problem. The example is, a company makes two types of furniture, chairs and tables. Profits are like rupees 20 per chair and rupees 30 per table. Both products are processed on three machines, M1, M2 and M3. It is known that each chair requires 3 hours on machine M1, 5 hours on machine M2 and 2 hours on machine M3, while each table requires 3 hours on machine M1, 2 hours on machine M2 and 6 hours on machine M3. During 1 week, the first week, the company has 36 hours on machine M1, 50 hours on machine M2 and 60 hours available on machine M3. Now, how many chairs and how many tables should the company produce over the week in order to maximize the profit? So, this is the problem. Many problems involving decision making under certainty, including this one, are solved using a technique known as linear programming. Now, we'll see the second type, decision making under uncertainty. If a decision maker is faced with choosing one action from among two or more alternative actions, and each of these has a possible outcome that depends on the chance of occurrence of one set of mutually exclusive and collectively exhaustive states of nature, the decision maker is said to be faced with decision making under uncertainty. This decision making under uncertainty involves the selection of a course of action when we do not know with certainty the results that each alternative action will yield. In other words, we assume that the outcome of whatever course of action the decision maker takes is affected only by chance and not by his opponent or competitor. We give below some examples of problems where business decisions must be made under uncertainty. So, examples are, the first one, a newspaper vendor buys a newspaper at rupees 2 each and sells them at rupees 3 each. Any papers not sold by the end of the day are completely worthless to him. His problem is determining how many newspapers to buy, enough to make a good profit but not too many to avoid loss due to wastage. The newspaper vendor is faced with a decision problem in a phase of uncertainty. Now, the next example is a company wishes to know whether an increase in the amount of flavoring in toothpaste will increase the sales. If the flavoring is increased and sales do not increase appreciably, the company will lose money due to increased cost. If it decides not to increase the flavoring when in fact it should have, it will have a lost potential sales. The company is faced with a decision problem in the face of uncertainty in this case as well. Now we'll see the next example. An oil company wishes to know whether to drill for oil in a particular location. How likely is oil there? How much? How deep will they need to drill? So these are the problems he will face. Next example. A financial firm wants to invest in securities. The problem of the firm is to determine which are the market sectors and individual securities with the best prospects. Where is the economy headed? How about the interest rates? How should these factors affect the investment decisions? So again, these are the problems you'll be facing. Now we'll see the third type. This is decision making under conflict. Decision making under conflict is similar to decision making under uncertainty in that we do not know with certainty the results each available alternative course of action will yield. However, the reason for this uncertainty is different in the case of decision making under conflict. In fact, in decision making under conflict, the outcome of our chosen course of action depends on decisions made by our competitors or appointments. Decision problems of this type fall under the discipline known as game theory. The discussion of game theory is beyond the scope of this text. However, an example of this type of decision problem is illustrated as follows. The example is, a television manufacturer is currently facing a decision about the price of TV it makes. If the company sets a price too high, potential customers will purchase competitors' TV. If on the other hand, the price is set too low, the competitors will also drop their prices, thereby reducing everyone's profit. This example concerning the decision of whether to change the price of TV demonstrates decision making under conflict. Decision making under uncertainty. So some of the basic concepts we will discuss here. In this section, we shall identify and discuss some of the basic concepts common to all decision problems under uncertainty. The first one, actions. Every decision maker is faced with choosing one action from among two or more alternative actions or strategies. We refer to these alternatives or strategies as acts or actions. The decision maker has control over the choice of these acts or decisions. The m possible courses of action available to a decision maker are usually denoted by like A1, A2, so on, AM. States of nature or events. The outcome of the decision maker's chosen course of action depends on certain chance factors that are beyond the control of decision maker. We refer to these factors as states of nature or events. It is assumed that the decision maker is aware of the whole list of events like S1, S2, so on, Sn, and exactly one of these is bound to happen. In other words, the n events S1, S2, so on, Sn are assumed to be mutually exclusive and collectively exhaustive. Now we'll see what is outcomes or payoff. The reward or penalty corresponding to each action or state of nature combination is called the outcome or payoff. An outcome may be either positive or negative. It may be noted that a payoff is conditional value because its value depends on the event that occurs and the action which is taken. Payoff tables or matrix. A payoff table showing conditional payoffs resulting from all possible action or state of nature combinations. The journal form of a payoff table for a decision problem involving m possible acts like A1, A2, so on, Am, and n states of nature S1, S2, so on, Sn is shown in table 1.1. Each of the set of possible actions the decision maker has chosen is associated with a row of the payoff matrix. Each state of nature is associated with a column. For example, the number of oil is the outcome resulting from the combination of the ith action with the jth state of nature. In order to analyze a decision-making problem, we should first write down all possible acts and their corresponding payoffs. This is demonstrated in the following examples on inventories. The example is a retailer has a space for 4 units of a particular perishable product per week. The cost of a unit is rupees 30, the selling price is rupees 50 and the profit is rupees 20. Any units not sold at the end of the week are wasted. The retailer does not know the demand but must nevertheless decide on the number of units of stocks. Write down all the possible acts, state of nature and the corresponding payoffs. So let's see the solution. We have a table here 1.2 which shows the payoff resulting from all the possible combinations of actions, number of units stocked and events, that is number of units demanded. Opportunity loss or regret. The opportunity lost is defined as a difference between the payoff a decision maker received for a chosen action and the maximum that the decision maker could have received for choosing the action yielding the highest payoff for the state of nature that occurred. For example, suppose the retailer in example number 7 had stocked 2 units, but that 4 had been demanded. His actual profit from selling the 2 units which he had is rupees 40. If he had stocked 4 units, he would have made rupees 80 profit. Thus, his opportunity loss is rupees 80 minus 40, that is rupees 40. So, it may be noted that opportunity loss can never be negative. The loss for the best possible act is 0. For all other acts, the loss is always positive. Now, let's see opportunity loss or regret table. An opportunity loss table is a table showing opportunity losses or regrets due to imperfect information. We next show how to construct the opportunity loss table from the payoff table by repeating the following 2 steps procedure. And the procedure is, the first step here, find the maximum payoff for a given state of nature. The opportunity loss associated with this payoff is 0. Step 2, the opportunity loss associated with any other payoff for this state of natures obtained by subtracting that payoff from the maximum payoff from that state of nature. Now, let's come to see another example. Construct the opportunity loss table for same example number 7. Now, we'll see solution to this, like the payoff table for example 7 is reproduced here for ready reference. We derive the opportunity loss table with the following 2 steps procedure again. Step 1, for each column of the profit table, table 1.3, mark the maximum payoff with a star. The opportunity loss associated with each column maximum is 0. Step 2, the opportunity loss table is constructed column by column by subtracting each value in table 1.3 from the started value in its column. The resulting opportunity loss table is shown in table 1.4. Now, we will see the next topic, that is solving the decision problem using the expected payoff criteria. We will see the next topic, that is solving the decision problem using the expected payoff criteria. We have already seen how to structure a decision problem by constructing a payoff table, or an opportunity loss tables are useful in analyzing a problem, but they do not contain enough information to help one make an optimum decision. We now want to find a rule that determines which alternative is best under uncertainty. To determine which alternative is best under uncertainty, we must decide upon a criteria for choosing among the various strategies. Numerous criteria have been proposed, but the most commonly used in a decision analysis uses a payoff table and chooses the action that produces the maximum expected payoff. This is called the expected payoff criteria or expected monetary value EMV criteria. Equivalently, one could use an opportunity loss table and choose the action that produces the minimum expected opportunity loss. This is called the expected opportunity loss or EOL criteria. It can be shown that both criteria lead to the same solution. To apply the expected payoff criteria, it is assumed that the decision maker has some idea of the probability of each state of nature. These probabilities can be used in the decision process to find the expected payoff of an alternative. The expected payoff or expected monetary value EMV, or it is denoted by AI for the ith action. AI is defined as the sum of each outcome OIJ of act AI and state Sj times the probability of state Sj. Symbolically, EMV, that is AI, is equal to summation of OIJ times probability of Sj. In other words, the EMV for any act is the weighted sum of all the payoff for that act over different states of nature, that the weights being the probabilities of occurrence of the corresponding states of nature. Expected opportunity loss criteria. To obtain an optimum decision using the expected loss criteria, we use an opportunity loss table, find the expected opportunity loss for each action, and then choose the action that produces the minimum expected opportunity loss. As mentioned at the beginning of this section, this will always lead to the same decision as expected payoff criteria. Now, we'll see an example here. Give the following payoff matrix and give the probability of whether being hot is 0.8. Set up the opportunity loss table and compare the opportunity loss of each action. Select the best act. Let's see the solution. The opportunity loss table for the given payoff matrix is shown in table 1.5. Computation of expected opportunity loss EOL will be like expected opportunity loss for the act cell cold ring is equal to 0.2 times 70 times 0.8 will be equal to 14. Expected opportunity loss for the act cell hot drinks will be equal to 0.2 times 0.8 times 60, which is equal to 48. Since expected opportunity loss is minimum for the act cell cold ring, therefore according to EOL criteria, the act cell cold ring is the optimum or the best act. We'll see the next example. A group of students raises money each year by selling the souvenir outside the stadium after a cricket match between team A and B. They can buy any of the three different types of souvenir from a supplier. Their sales are mostly dependent on which team wins the match. A conditional payoff table is as under. So what we have to do is, first thing, that construct an opportunity loss table. Second, which type of souvenir should the student buy if the probability of them A winning is 0.6. Let's see the solution one by one. The first one, the opportunity loss table for the given payoff table is shown in table 1.6. So we are given the probability of team A wins is equal to 0.6. So that implies probability of team A B wins will be equal to 1 minus 0.6, which is equal to 0.4. Therefore, the expected opportunity loss for the act type 1 souvenir will be equal to 0.6 times 0 plus 0.4 times 850, which is equal to rupees 340. Now, the expected opportunity loss for the act type second souvenir will be equal to 0.6 times 400 plus 0.4 times 400 will be equal to rupees 400. Expected opportunity loss for the act type 3 souvenir will be like 0.6 times 900 plus 0.4 times 0 will be equal to rupees 540. Since the expected opportunity loss is minimum for the act type first souvenir, therefore by using the EOL criteria, we find that the act type 1 souvenir is the optimal act. In other words, the student should buy type 1 souvenir. Now we'll see in the next example. A company is trying to manufacture a new type of a toy. The company is attempting to decide whether to bring out a full, partial or minimal product line. The company has 3 levels of product acceptance and has estimated the probability of occurrence. Management will make the decision on the basis of maximizing the expected profit from the first year of production. The relevant data are shown in the following table, where first year profits in 1000 rupees are given. First part, what is the optimal product line and its expected profits? Second, what is the optimum value of expected opportunity loss and optimum course of action? Let's see the solution. Let us define the following acts as A1 as a full product line, A2 as partial product line, A3 as minimum product line. So first part of the question, to find the optimum product line, we'll use EMV criteria. We have EMV for A1, that is equal to 0.2 times 90 plus 0.4 times 460 plus 0.4 times minus 15 is equal to 36. Similarly, EMV for A2 will be like 0.2 times 80 plus 0.4 times 65 plus 0.4 times minus 10. So that is equal to 38. Now EMV for A3 will be like 0.2 times 60 plus 0.4 times 50 plus 0.4 times 0, that will be equal to 32. Since EMV is maximum for the Act A2, therefore by EMV criteria, the Act A2, that is partial product line, is the optimum act and its expected profit is EMV for A2 will be equal to 38,000 rupees or 38,000. Second part of the question, to find the optimum value of expected opportunity loss, it is first necessary to find the opportunity loss table, which is obtained by using the following two-step procedure. First, find the maximum payoff for each state of nature. We have maximum payoff S1, that is good, is equal to 90. Maximum payoff S2, that is fair, is equal to 65. Maximum payoff S3, that is for poor, it's 0. Second, the opportunity loss table is constructed column by column by subtracting each value from the maximum value in its column. The resulting opportunity loss table is shown in table 1.8. So therefore, EOL of A1 will be equal to 0.2 times 0 plus 0.4 times 5 plus 0.4 times 15, which is equal to 8. Similarly, EOL for A2 will be 0.2 times 10 plus 0.4 times 0 plus 0.4 times 10, which is equal to 6. Then EOL for A3 will be 0.2 times 30 plus 0.4 times 15 plus 0.4 times 0, which is equal to 12. Since EOL is minimum for Act A2, therefore, by the EOL criteria, the Act A2 is, that is the partial product line, is the optimum act. The optimum value of expected opportunity loss is EOL of A2 is equal to 6,000 rupees. The reader may note that the EMV criteria and EOL criteria result in the optimum act. So finally, we have learned today the first part of the chapter of statistical decision theory. In this chapter, we have identified and discussed different types of decision problems and have learned to describe our decision problems in terms of decision alternatives, states of nature and payoffs. Also, we have discussed how to calculate or use payoff and regret tables to analyze decision problems. So that brings us to the end of today's episode. We are ending here the first part of the chapter of statistical decision theory, and we'll see you again discussing about our next part on the same topic on more wide variety. Till then, have a nice time. Thank you and bye.